This is the short summary for Chapter 2 of the Functional Programming tutorial. The focus of that chapter was on working with collections in the functional programming. Working with collections has a lot to do with data structures such as tuples and sequences. Tuples are a very basic data structure that is available in most functional languages. I explained how they work in Scala and how you can define functions that take tuples as arguments. Taking tuples and decomposing them into parts can be done using pattern matching syntax. Tuples are used very often in the standard library, especially in functions involving maps or dictionaries, and a very often used operation such as zip produces a sequence of tuples. I'll give a lot of worked examples of how one works with collections using various standard library functions such as map, count, zip, sliding for the sliding window, flat map for concatenating lists inside lists, max, toMap, which creates a dictionary, and so on. I give exercises to drill this material. Now we look at how mathematical induction is mapped into code. We recognize that, for instance, a problem such as compute an integer value given a sequence of decimal digits cannot be solved using functions such as map or filter. It requires mathematical induction because we don't know how many digits there are. Mathematical induction can be translated into code in two ways, either by directly using recursion or by using standard library functions such as fold, scan, and so on. First, I look at how to use recursion by hand. Here's an example of a recursive function called fromDigits. It calls itself. I explain how this function works and show that this is not necessarily very convenient. Also, this function is not stack safe. It could give a stack overflow. I explain why that works, why that happens, and how to fix that. To fix that, you need to use the so-called Taylor recursion, which is I show how that works in Scala, and also I explain how to convert a recursive function that is not tail recursive to a tail recursive ways. In certain cases that can be done using the so-called accumulator technique. The second way of writing mathematical induction is to use a fold function, such as fold left. And the fold left directly translates mathematical induction. It gives an expression with two arguments, or a function with two arguments. The first gives the base of induction. The second gives the step of the induction. So that's the direct translation of mathematical induction into code. And this function is tail recursive. So this is a somewhat easier way of writing general mathematical induction as a program. Another typical problem is to compute a sequence out of a single number. Now, these functions don't work for that because they require an initial sequence, and we don't have that. We have a number as a starting point. So that requires a function such as unfolding. Here's an example. Compute the sequence of decimal digits of a given integer. For that, I explained how to use an iterator. So Scala standard library has this concept, and I show how to do that. This is a functional way of doing that. So as you see, there are no loops. Another typical problem is to compute a sequence out of another sequence. And that is again defining by induction. The standard library function for that is scan. It takes two arguments, the base of induction and the induction step, and it yields a sequence of partial results. So using these tools, we can translate mathematical expressions involving mathematical induction into code. We can use tail recursion when possible, and we can transform sequences in very flexible ways using standard library functions such as fold and scan, also iterator. Problems that are not solved with these tools are non-tail recursive functions for which the accumulator trick does not work. So those cannot be converted to a fold, and those functions need more advanced methods for their treatment, which are not covered in this tutorial. I give some examples of using fold, iterate, and other standard functions of the library to solve various problems with sequences that require mathematical induction. And I give exercises that drill this material.